The very last section in this lesson is we're going to talk about a relationship between the DFT, the DTFT, and continuous time. And in particular, we're going to talk about the relationship between the index of the DFT, K, the index of the DTFT, which is omega, and the corresponding frequency in the time domain. I don't know why it's not in most textbooks, but I'll tell you what it is. The relationship is F is to F sub S. This is the actual frequency in the time domain versus its sampling frequency is a fraction, which is proportional to the omega of the DTFT relative to 2 pi, which is proportional to the index K of the DFT relative to the number of samples. This equation is incredibly useful. So just as a quick example, say you're sampling a process and you're sampling it with a sampling frequency of 1 kilo samples per second. So you're sampling at 1 kilohertz. You think there's something odd going on. You want to see how much sound energy there is at a particular frequency. Maybe you're interested in listening to the sound of a bearing rumble, and if it's a bearing in a big power generation unit, and if it's rumbling at 60 hertz, that means that bearing might be failing soon. You can't hear anything. If there is any rumble, if there is any whine at 60 hertz, it's a very small amount. So you take maybe 10 seconds worth of data. So you take it for 10 seconds, and that means that and the number of samples you've collected over 10 seconds, if you're collecting at 1,000 samples a second, you've collected 10,000 samples. And you take your X, this is your data, and you plot it, and it looks just kind of rumbly and noisy, and you can't really make much out of it when you plot it, not surprisingly. But you want to see how much energy there is at 60 hertz. So you stem the absolute value of its DFT computed using the FFT algorithm, and you see, not surprisingly, that there's a lot of noise around here, and it's kind of hard to see anything. But sure enough, you do see kind of a spike here, and you see, there's got to be mirror image here. So you see a spike over here. This is the stem of the FFT. You could say in math terms, this is the absolute value of your DFT. And we've got points going all the way up to, since you're starting off at 0, you've got points going all the way up to 9,999. But there's definitely something going on at these 2 points. Now, you're not interested in this because this is going to have to be just the complex conjugate of this. It'll have to be mirror symmetry around someplace in the middle of this. But this is going on at K equals 279. So you'd like to find out what is the continuous frequency that corresponds to 279, because if it's 60 hertz, there's a bearing failure. So you use this equation up here, and you say the frequency relative to my sampling frequency, which was 1,000, is equal to my K value, 279, divided by my N value, 10,000. And from that, you can find that the corresponding frequency was 27.9 hertz. And you can say that's not your bearing that's going bad, it's something else happening. This explains why you're taking DFTs. You're taking DFTs not because you're really interested in this weird thing with mirror symmetries around the pi equivalent of the DTFT thing from which the DFT was sampled. My goodness, the reason why you're doing it is because you want to find insight into a continuous time system. The DFT gives you that insight, and then this equation lets you back that out to find out what the corresponding frequencies are.